Does anybody have any issues with Packet Tracer in terms of having to log in every time? I mean, everyone is able to log in and everything.
I do. Like it takes like I've been able to do it like here and there, but a lot of the time it'll like for some reason it'll time out or like it'll start, but it'll pop up like this thing called like skill for all
Mm-hmm.
or
I just do skill. I always go through skills for all because before prior to this semester starting, I was on this. I had changed computers. I had changed laptops, so I had to install Cisco Packet Tracer all over again as if I had never used it. And I did notice that when I do have to log in, I do Cisco Skills for All. It didn't used to be like that. Cisco's always changing up their Packet Tracer website, so it's literally different every time. That's why I don't really put instructions on my syllabus on how to download it and install it and everything, just because it changes every time. It literally changes.
right.
So hopefully
I also
everyone's
have
still
one.
able to log in.
It's not with logging in. Mine is like when I open it and I try to like edit something inside it, like it would let me the first time, second time it would just not let me type anything. And I have to like play like exit it out or do something. I don't know, is it my laptop or it's Packet Tracer?
Oh, okay. Yeah, sorry about that. It's not perfect, but how many people would agree though? It's a great, great tool. I mean, I think it's a
It
fantastic.
is.
Yeah, I think it's
Yeah.
I think it's a fantastic tool, and the fact of the matter is, it's free. I mean, I can't believe it's free. Um, it didn't always used to be free. Back in the early 2000s, when Packet Tracer was in its infancy, you actually had to pay for Cisco or excuse me, Cisco Academic. What they used to call it, Cisco Academia or something like that, or the Cisco Learning Network or something like that. So you had to, in the classes were like hundreds of dollars. So essentially, you're paying hundreds of dollars for Cisco Packet Tracer, and people were doing it because it was just an awesome. It's just an awesome tool. Then all of a sudden, it became completely free, and you could just download it and install it, and there was no logging in or anything. And then they made it so that it was still free. It's not like it is now. It's free, but you had to create a login into Cisco Academic or whatever it is, the Cisco Learning Network, and so the cost is like potentially your privacy, but the cost is essentially all you have to do is just receive emails from Cisco occasionally, and it probably just gets shuffled out into your marketing spam folder or your marketing folder or whatever. Anyways, so it is what it is. It's still free. You just the only cost is a few emails here and there, and to me, it's a wonderful piece. It's not perfect. It does not have all the commands that an actual router has, but it's got a lot of them. It's got the most meaningful ones for our purposes. If that makes sense. So that's why I like it. Anyways, let's get down to business. I'm gonna go ahead and share my laptop, share my desktop, I should say. Hopefully everyone sees everything. I'm just gonna get down to business. It's hard for me to get down to business when everyone's like coming in. I have to admit every single person. So, anyways, hopefully that's it. So as I said, this is going to be recorded. So I'm starting off with 192.168.1.0/24, and now I want to subnet and I want 20 hosts per network. Okay, so how many networks can I have? How many networks can I have? So I want everyone to freaking do this right now. Somebody take a couple minutes and work it out, okay? Um, and work it out. And then I'm going to give everyone 5 minutes, and then you're going to work it out. And then I am going to talk about what the solution is. But the most important thing is just not the solution. It is how we get to that solution. So I'm going to give everyone a few minutes. Hi, Andre. You've just logged in, or you just got in. Right now, we're working on this problem. 192.168.1.0/24, so it's a classful C IP address. We want 20 hosts per network, and the question is, how many networks can I have? So that's what we're working on, Andre. So just think about it for the next 2 or 3 minutes. Okay. Who can tell me how many networks can I have with this classful C IP address with the classful C subnet mask? And unfortunately, I have to let in more people. So somebody tell me how many net... Oh my God, these people. Okay, so somebody tell me how many networks can I have? Somebody tell me. Well, at least tell me if you don't know.
5.
Somebody don't. Okay. Oh. I'm sorry. D1 James or Dantes. Did one of you say something? 5.
Yeah, I think that was D1 James.
Okay, D1 James. You actually said 5.
Yes.
Yeah. Oh my. That's darn close. What I think D1 James was actually saying, or what he meant, was if we want 20 hosts per network, okay, that means that we have to reserve 5 bits for 20 hosts on the network. Okay, so if we reserve 5 bits if we reserve 5 bits for the host, and like pretend like we didn't have this here. Let's just say we inserted. Let's just do 8. Okay, 20 hosts per network, and there's 5 bits left over for the host. So that is 1. We'll just say H. So there's 5 bits left for the host, which is 32 total hosts. Okay, let me write it down here. 32 total hosts. First off, how many usable hosts per network are there? And just so everyone knows, I'm referring to this right here. 2 to the 5th. Let me get my drawing tool out. 2 to the 5th is 32 hosts per network because we're reserving 5 hosts for 5 hosts per network right here. So 2 to the 5th is 32 total hosts. How many usable hosts per network do we have? Remember, this is going from all zeros to all ones. So in other words, if one of our IP addresses is something like this, so this IP address will be 192.168.1.64, okay, and 64 plus whatever this is. So if we had a network somewhere in here, we'll call it 0, 0, 0, 0, 1 for the heck of it. Okay, so that would be 64 plus 1, that's .65. So it would be in the .64 network. So if we have 2 to the 5th, 5 bits left over for the host, how many for the network? How many bits for the network do we have?
8.
3.
2 to 3. 2 to the power of 3, I mean.
Yes, that's 8. 8 total networks. So we could do something like this. We can have a router. We can have a network separating device here, or a router. We can have a router here. And we can have a router here. And then we can connect another network here. So, and then that's one network. That's 2 and 3. And then we can connect we can have a LAN here. So that's another network. That's 4. We can have another network here. That's 5. Another network here. That's 6. So this topology works if we borrow 3. That's a /27. So if our requirements are 20 hosts per network, how many networks can we have? Can we possibly have? The maximum amount of networks is 2 to the 3rd or 8. Now, right now we're using 6, but that means there's 2 plus for growth. So we can have support 2 more networks for growth. So what could eventually happen is, let's say this company, maybe they're Acme, and let's say they buy out another company. So that gives them the opportunity to add 2 more networks here and another LAN right here. So that's the max 8 networks, if this makes sense. So let's go ahead and actually create something like this. Okay, so we're gonna go to our network devices, click on that, making sure we clicked on it, and then we're gonna drag our routers right here, and we're gonna make it a little bit bigger, and then we're gonna drag our router here, and then drag our router here. So we have a couple routers right here, 3 routers. We're gonna go to our connections, and then I'm just gonna connect one because I don't want to take up too much time in doing this, and we can grab. So I'm just gonna delete this router right here, because I'm not gonna do the entire thing because I don't want to take up too much time. And what I could do is put a PC here, and put let me go back to these network devices. Let me go to see how I'm grabbing a switch right there. Let me just put a switch here. And then from here, we can add a loop back, and let me just no fill. Let me just delete that. So you know what? I'm just gonna drag this here, and I will call that this loop back right here, and we'll have a physical interface here, just so everyone can understand that there are logical and physical interfaces. So we have an interface here. We'll do FA10, and we'll connect this here like this. F20. Okay, and let me very quickly go through this. We'll make this the .1, the .0 network. We'll make this the .32 network, and we'll make the loopback the .64 network. And then we'll do everything progressively. So this will be .1 and this will be .2. So let's go to this PC, and let me go to desktop, IP configuration, and 192.168.1.2 with a 225, 255, 255, 224 subnet. Does anyone not understand why I am using the 224 subnet mask? And please, somebody tell me if they do not understand. This is the time to say I don't understand.
Explain it one more time.
Okay, good. Okay, so these devices need to communicate to each other the IP address scheme. So when we say 192.168.1.0/24, when we borrow 3 bits, that becomes /27. So what we are saying is that this is the IP address scheme. You understand what I mean by scheme? What I mean by scheme is almost like a pattern or things that we can do. Kind of like if you started a business. Somebody said, hey, I got a scheme for it. And I don't mean, the unfortunate thing about the English language is that unlike other, we attribute negative things to things that should not be negative, like the term agnostic. When we talk about agnostic things, one second, somebody's trying to join in. It takes me off my game when I have to do this, but it is what it is. When somebody takes the, let's say the word agnostic, there's a negative connotation to the word agnostic, especially if you talk to somebody that is traditionally religious. But all agnostic really means is the term agnostic is that we're not beholden to a certain belief or something like that. Okay. So the term scheme, some people attribute that to be a negative thing, like, oh, I have a scheme. We're scheming against something. It's like, no. All I want a scheme is like, what is the pattern that we're building? Like, what are the IP blocks that we're building? But the problem is that needs to be transmitted or communicated to devices all around you so everyone knows what you're doing. And the only way we can communicate what the intended IP blocks are, okay, or what the intended networks are, is the subnet mask. The subnet mask does a lot of things. It defines where we can go. So based using /27 in terms, that's what we call dotted that is what we call CIDR notation. The slash CIDR is, and let me write that down so you know what I'm talking about. CIDR. That's called CIDR. It's called classless interdomain routing. So what it means is that classes A, B, and C are meaningless because we haven't used classes since like the late 80s, 1980s. Like some of your parents were probably born when when classes actually meant something. So the /27 tells more about the IP address than the IP address itself. /27 means that we divide our networks by 32s. 0, 32, 64, 96, right? And we know that because of this. 1, 2, 3. 1, 2, 32, 3. But how do we communicate this? We use CIDR notation. Okay, /27. But we communicate it to the computers with the subnet mask. Now, as I said before, computers themselves do not understand things like /27. They don't understand zero. All they understand is zeros and ones. So when you think, so for example, we look at this /24. /24 is simply 255.255.0 because there are 24 ones in that default Class C subnet mask. Because for every 255 is 8 ones. 8 ones. 8 plus 8 plus 8 is /24. But we want to add 3 because we want to create 8 networks within our global subnet. And so we have to say, since we add 3, it's 24 plus 3 is 27. But how does this PC, how do we configure that /27? This is where your binary to decimal skills come into play. If we're adding 3, okay, so that's 1, 1, 1, and then all the rest are zeros, 5 zeros, so it's 128 plus 64 plus 32, and that's all we add. So 128, 64 plus 32 is, anyone? 224. Okay, does that make sense? Well, if it's not making sense, yeah, but if it doesn't make sense, I just sleep on it. And all I can tell you is that you're going to have to work on it. And you're going to have to do subnetting problems in your free time for you to really understand. Okay. Looking back at this, it's 224. The default gateway for this PC is going to be this default gateway. So it would be 192.168.1.1. Did I say this default gateway? I meant the default gateway for this PC would be the IP address of the inside interface of the layer 3 device. And that is, in this case, router 0. Now, at your home, your default gateway probably is your modem or your gateway that you get from Xfinity or WoW or whatever. And that is because that is the inside device, the edge device, before it NAT overloads to your WAN IP address. Okay, let's go to this router. Let's do it as quickly as possible. We're going to go to the command line interface. And, sorry, let me just do it like this. Move this over. Okay, now, anytime it says, do you want to automatically configure? We're going to type in no. Press return to get started. Where are we at in the command line interface? What prompt is that? The greater than sign, what is that? The user mode. And I want you to think, link user to useless. Okay, we can't really do anything. We at least need to get into the enable mode. So we type in enable. Press enter. Now we're at the pound sign, which is the executive mode or the enable mode because you type in enable to get to it. Now, here, 1 second. Now, to get back to the user mode, we type in log. What did I do? Did I say log out or log off? Now, I want you to. I just did that because you can also just type in en and enter to get into do the same thing because there's no other. Because Cisco routers use contextual syntax, like your cell phone, I guess. Now, to get to this interface, we have to get to first get to the global terminal. So we type in configuration terminal. Enter. Now, now we got to get to that to this interface right here, int f1/0. First thing we do no shutdown, or we can just do no shh like that. Okay, I like to say that, no shh like that. Okay, so now we can do IP address 192.168.1.1 with a 255.255.224 subnet mask to communicate that, hey, since all the networks, the scheme or the IP blocks is 32s, then we have now an understanding with this router that it's essentially divvying up these networks in 32s. This router here, and this router here. So this is the .0 network, this is the .32 network, and this is the .64 network. And even though I'm drawing one line here, in reality, every single interface of a router is its own network. So if you click on this router, and for example, well, we can do show IP interface brief, or IP int brief, or BR. We can see all of our interfaces there. And every single solitary interface has to be in its own network. Why is that? Because that is what a router does. That's all it does, is it separates different networks. And it also separates different technologies. So as you can see here in this router, we have fast Ethernet. Now fast Ethernet goes 100 megabits a second. That's the bandwidth. Serial ports. Unfortunately, that's slower. That is that's multiples of 1.54 megabits a second. So we're going from 100 to 1.5. That's a significant slowdown. Well, some of you might be like, well, why do you even have these? Well, because these enterprise networks that you will run into if you ever get a networking job, some of these networks have been around literally since the 80s. And in the 60s, 70s, and 80s, WAN connections were all serial based. Now you'll hear things like T1 and T2 and T3. Those are speeds, link speeds. So when somebody says, well, we're hooking up a T1 line, that means that it's a very slow, I'm going to say retro type connection, or legacy type connection that's still around. Well, why is it still around? Here's why it's still around. Okay? Let's take a look at what this router actually looks like. We click on it, and we can go to the physical, I think, and that's what the back of the router looks like. Okay, I wish it showed the front too. You know, it'd be nice to see the front, but this is what the back looks at. And you see, these are removable modules that you can take out at your whim. So here's the fast Ethernet 01 connection. Okay, let me go back to here. Yeah, 00 and 01. That's 00 and 01. This is fast Ethernet 4 and 5. 1, 2, 3, 4, and 5. See how the numbering system is? 4, 0, 5, 0. So that's 1, 2, 3, 4, 0, 5, 0. And you can see that's high speed. FFE. We can take a look at FFE. One fast Ethernet interface for use with fiber media. So that's a fiber connection. Okay, so we can talk about fiber connections on another day, like possibly the next day. But we can see that this is 100 megabit. This is 1.54, multiples of 1.54 megabit a second. And this can go basically 1,000 megabits a second. So that's gig speed right there. And the problem is, you might say, well, why are these even in here? Just throw them out. If you're in an enterprise situation, if the other connection is a serial connection, then you're stuck. You have to order these connections to match the other side. And you're like, well, contact the other side. But what if the other side has legacy equipment that only uses serial connections? That's a thing. And let me just talk. Let me just give you an example of what man, this is horrible writing right here. I'm sorry. So here, let's say you're in a situation where this is the side of the router, right? And here you have a fast Ethernet connection here. I'll just say F for fast. And then here, you have a serial connection. You're like, well, wait a second. Let's just replace the serial connection and add something else. But what you're connecting to, it might be a legacy type company or a legacy type equipment, and all they have is a bunch of serial connections. And at one point in time, they did. That's all there was of serial connections. So you're kind of stuck, because when you're developing a network, you actually have to match the technologies in order for both sides to communicate, because this is connected to a LAN, this is connected to a LAN. So you got a lot of computers and people that are counting on the successful exchange of information. And when I'm just drawing these so that they're only a few inches apart, but this could be replicating a global network. This could be North America, some data center in North America, and this connection might be a small data center in Asia. You know, Ford has dealerships and they have offices all over the world. So you got some third world countries that only use legacy equipment because they honestly can't afford anything else. And the other problem is it might be using a device that's linked to another device that can't be touched. Like a lot of, for some reason, a lot of actual assembly line and production equipment uses all legacy equipment. Like literally, the assembly lines, like in Trenton and all that. You might walk into their factory, although you wouldn't be allowed. But if you walk in their factory, they might even be using Windows 2000 servers. And you guys are like, well, wait a second. Why don't you just upgrade, right? To at least Windows Server 2016 or something. And the answer is, what do you need to upgrade? You need a window for downtime. And then you need a window, you need people there to make sure it runs smoothly, that it doesn't go down, because if the assembly line goes down, that's like $1 million. That's like $500,000 an hour or something. So the problem is, these guys try getting a window, because there are no windows, because the assembly line's always going. So that's why there is still legacy equipment. I hope in that long-winded explanation, I hope I explained it to you. As if you guys nobody even asked, I just told it. So anyways, so this network now, this divides our network by 32. So let's go back in here. And go back to the command line interface. Okay. Now we're going to go to this other side right here. And that's FA00. So we're done with this one. I think. Yeah, we are done. We did F10. Now let's do, and then we can do a description, and then we can say something like zero network. Like that. That's our description, zero network. Here, let's do interface F00, no shut. And we can do a description, and then we can say 32 network. And let's put an IP address 192.168.1.33, 255.255.255.224. Go to end, and we can do show IP interface brief, and we do have our IPs on here. Notice when we do show IP interface brief on the .0 network, status is up, but protocol is down. Here on F10, we have up and up. Now, can somebody tell me why the protocol is down? And also, what protocol are we talking about? What do they mean? What protocol are they referring to? Somebody tell me. Why is it up, down? Well, I'll just explain it, because it's because the protocol we're talking about is Ethernet. And in order for the Ethernet protocol to be up, both sides at least have to be powered up. So I'm going to go ahead and at least, you know what? I'm going to go to this router now, and I'm going to go to F configuration, physical config. I'm going to go to F00. I'm just going to turn it on from the UI, and then I'm going to go back here, and then now you can see. Let me run it again. And now you can see the protocol is up and up after I ran show IP interface brief again on this first router. All right, let me go back to this router. And let me get to the command line interface. And let me type an X to get back. Let me make sure I'm in the right interface. Int F0/0. And it's already up. I don't need to do a no shut, but guess what? I'm still going to do it. You can never do no shut too much. And then description is 32 network on this side. And then we're going to do IP address 192.168. Let's do the last available network on here. Let's do the last available IP address. Can somebody tell me what the last usable address is for this .32 network?
Is it 1.1?
No, we're on this side now. What's 32 plus 64? Oh, I'm sorry, what's 32? What will be the next network?
192.168.
60, you mean 64?
Is it
Right.
96?
Well, no. What's the last usable network for 32, for the 32 network? Remember, 32, remember I said we go up 0, 32, 64, 96, remember that?
Yeah.
So what's the last available IP address for the .32 network? If the next network starts at 64, what's the last available of the .32 network?
Is it?
We went over this. Is it 63? Can somebody tell me whether it's 63?
I would say 63, but I'm not sure with like broadcast
Okay, that is the broadcast. So we know we can't use a broadcast because 63 is the broadcast address of the 32 network. So we cannot use .32. We can't use .63. So what's the last usable IP address? We went over this. Come on, guys. What is the last usable IP address? So if our network goes .0, .32, .64, and then if we extended this, it would be .96, and if we extended it even more, it would be 128. Okay, so our networks inside here, our usable networks are from .1 all the way to .30. Okay, we've established that. We can't use .31 because that's a broadcast network. So we can use .1 and we all the way to including .30. So what are the usable addresses of the .32 network? Come on, somebody. We went over this.
33 to 62.
Yeah, very good. So we're gonna make this .62. So let's go back to this router. So .1, .62 with a 255.255.255.224 subnet mask. Now this is our loopback address, and this is the .65 network. So loopback address is like a virtual address. It's just an electronic address, you could say, that we make ourselves. It's kind of like the virtual IP address. I would call it the ghost kitchen, if you will, of addresses. How many of you guys do you guys know what a ghost kitchen is? Like, wait a second. Yeah, a ghost kitchen. And I just heard this. Go on, sorry.
It's like okay.
Go on, tell me.
I was gonna say it's like a restaurant, but it's like another restaurant inside of that restaurant.
Absolutely. So, in other words, we know now we don't have to have, for every restaurant doesn't have to have a brick and mortar address. They can make all the kinds of restaurants within restaurants. For example, you could have a sub shop, but maybe you can have a ghost kitchen in which you can have let's say it's a John Smith's sub shop, but then you can have a ghost kitchen that's Ed's Wings. So all you do is make wings in that ghost kitchen. Similar to this IP address, there is no physical interface, but we can make a logical interface electronically. Now, why would you want to make like a virtual interface? Why would you want to do that? Well, it's very helpful with using other protocols. Maybe not this one, but so I just want to demonstrate it to you. We can do it. So we're going to go int L1. And notice L1, we made loopback 1. Now the 1 is insignificant. We could use, we can go from 1. I've seen 30, 40 loopbacks on a router. So, and the other good thing about loopbacks or virtual IP addresses is that it's already up, so we don't have to do no shutdown because it's already up. But all we got to do is assign an IP address. And actually, we can do a description 64 network. And then IP address 192.168.1.65 with a 255.255.255.224 subnet mask. And end And then we could do show IP interface brief. And we can see that we actually have the loopback listed as an actual interface. So some of you were like, why was I doing the description? So if we do a show run, and let me just see, running configuration. If this is a real router, we can do interface F00, but it won't allow us to do that. Let's see if it can do include. So show run pipe include, and it doesn't do it. Oh, darn it. So let's just do show running configuration. And then you see the advantage of the description. When we use the description, we can actually see if we want to find out what network the loopback was in. We can see that the network is the .64 network, but we can put anything we want in that description. So that's the advantage of that. Anyways, so does anyone think that I should be able to now ping, let's say the loopback .65 from PC0? Let's see what happens. And it won't. But let's just try. Destination host unreachable. So what do we do when we're trying to troubleshoot? We just start from our local and then we branch out. So let's see if we can ping our default gateway. 1.1, and we can. Let's see if we can ping FA00. That would be 33. And it does. It's actually pinging this side. Let's see if it could ping FA00 on this side. This was .62. And no, it's not pinging. So what's missing? Someone tell me what's missing. What's missing, guys?
All right, which one was you trying to ping?
The loopback on router 1.
Did you assign the loopback IP?
Yes, I did. I can see your wheels turning, and I like it. What we're missing is the routing protocols. So going back to what we were talking about, routing protocols are what we call neighbor-to-neighbor protocols. So you have two routers directly connected to each other. And then you have, I'm just going to say, network A, network B, and network C. So this router needs to communicate the networks that is directly connected to it. So, for example, this router knows how to get to network A, and it knows how to get to it, and it knows it needs to go this way to get to network A because of the routing protocols that have been assigned to it. Okay? We went through that last week. But, okay, so all we have to do is go to our router right here. Go to Enable. Go get to the global configuration mode. And then we're going to use router. And then if we type in question mark, we can see the routing protocols that are currently available to us. And we want to use the oldest routing protocol, RIP. So RIP. And then we put in our networks. And the only network we are going to broadcast is 192.168.1.0. Okay, that's it. I typed end to get back to the pound sign. It's just a superstition of mine. And here, we're going to do the same thing. Configuration terminal. And router RIP. Network. 192.168.1.0. End. Now the good thing about RIP is that it is quick to converge and quick to, it is quick to act, I guess. It's like creating an algorithm, if you will. So we're going to go here, and we can run some commands, show IP route. And now we can see that it has learned about the 64 network by RIP. That's R for RIP. And we can see R is for RIP. And the only other routing protocol we're really going to be dealing with is OSPF right here. But we're a bit away from OSPF. So this is RIP. And now we should be able to ping .65. Let's go back to our command prompt right here. Ping 192.168.1. Oh, did I say 62.65? And we're able to ping it. Okay? And actually, yeah, that's why I tried to ping once it was 62, because it was on this side of the router, so we can even do that. So let's go back to command prompt. Obviously, that'll work because 65 works. Do 62, and there we go. Okay. Does everyone understand this?
Yep, I understand it.
Okay. We understand it, but there's an issue. There's an issue. I just got through saying that if we borrow 3, making this /27, it satisfies a requirement for 20 hosts per network, because technically there are 30 usable hosts per network. Hold on. I just heard something. I just heard Google Meet do something. Okay. All right. And just so everyone knows, we might get kicked out. So if we get kicked out, no worries. Now, what's the problem? We got 30 hosts per network. Looking at this, what is the problem? What do you think the problem is? What do you think the problem is? I mean, this is 30, so 30 usable hosts. So we got 30 hosts here, 30 hosts here. And I want you to imagine this is like a loop back, but just imagine that this represents a LAN. So, and this is 30 hosts. Now, there's only one host here, but don't you think if this is a LAN, it's going to grow? Call this LAN 1. And this is LAN 2. So it's going to grow. And does this represent a LAN or a WAN? Let's say it represents a WAN. Because this LAN 1 could be, we'll call it Auburn Hills. And LAN 2 might be SHAP, Sterling Heights Assembly Plant. So then they're in different parts, but what does this represent? This simply is a connection. Hold on, I want to make sure I don't get kicked out. Okay, we're still together. If this quits, Google Meet quits, I'm just going to have to redo it, and I'm going to have to resend everyone an invitation, and I'll do that if this quits. But wait a second. Why don't we do it right now? Let me close this out, and I have it recorded anyways. I have this whole entire session recorded. Let me close this out, And I want you to think about something. What is the issue? This is a WAN connection. So in other words, this is going to one tower, and this is going to a tower. So we have 30 hosts, 30 hosts, 30 hosts. 30 hosts? Do we need 30 hosts here? Now think about that. And I'm going to go ahead and quit this Google Meet. And then I'm going to resend the invitation for yet another Google Meet because they only give us an hour. Okay, everyone's starting to leave right now. So I'll be right back with another invitation. So everyone leave and wait for the next invitation. My courses. Hi again, everyone. Just waiting for more people to join. Okay, so I think we have enough people to really start. So what is the problem with this? And let me go ahead and share my screen. I don't even know if I was. Allow, share entire screen. Okay, so what is the issue with this? We have 30 hosts this side, 30 hosts this side, and 30 hosts this side. Now, the LAN 2, Sterling Heights Assembly Plant. This is only a mere representation of it, okay? But this LAN is gonna grow. Of course, it's a LAN. It's gonna grow. You'll have 30 hosts, okay? 30 hosts in here. But will this grow? This? Somebody? It's a WAN connection. It's still layer 2. It's still layer 2. I know it's strange, but when you're connecting two local networks in a WAN type situation, so when you're connecting Auburn Hills to Sterling Heights, and all you need is a point-to-point connection, it's still a WAN connection, but it's still layer 2. I know it's hard for people to wrap their mind around that, but it's still layer 2. But yet, It's a point-to-point connection. I'll even write it here. Point-to-point connection. Now, it's not a point-to-point protocol, right? Ethernet is. Ethernet is not at point. But here, it's simply point-to-point. So, will this LAN grow? Yes. Because this is just a representation. You can. There's only one host, but you can have 29 more. No, we can have 28 more hosts because that actually is a host. The interface takes up an IP address. So you can have 28 more hosts. Here, that's why I kind of represented this as a loopback address. That's its own network, but you can arguably have 30 more hosts if you take this away and add a network switch and add all these other PCs. This, I cannot emphasize this enough. This is point to point. You only need one side matching the other. That's all you need. So my question to everyone again is, will this grow? Mentioned to you before, this is a LAN that can grow. That's a local area network too. This will grow. Can this grow? What does everyone think?
You talking about the LAN connection?
The WAN connection.
The WAN connection, I don't think can grow.
There you go. Perfect. So do you see an issue with this? We only need 2 IP addresses, but we're borrowing 5 from each network, so this is going to have 30 hosts. Do you have an issue with that? Do you think anyone should have an issue with that?
You don't really need 30 hosts for that, right?
Absolutely, yes. I think you people are seeing the light. Yes, so it is such a waste of that, and I want you to think of subnetting, right? As like you're starting off with like one big box. Okay, let me just start a new page right here. So, for example, we start off with the entirety of your IP addresses that are available to us. So let's say right now, that's /nothing. So right now, this is a classful type network. So we're starting off with a /24, which if you take a look at this right here, okay, /24, because you know how our networks are, we got how our default subnet masks are /16, /8, and /24. So if it's a /24, we look back and we're not borrowing any. All right, if we borrow 3, we're making 8 networks. If we're borrowing 0, it's just one network. So the whole network is for us. So how many hosts can we have when we're not borrowing anything? So how many? We have 8 bits. And 8 bits is 2 to the 8th. And that is equal to 256 possible hosts total, which translates to 254 usable hosts. So basically, the whole enchilada is at our disposal. /25. So in this case, we're borrowing 1. Okay? If we borrow 1, okay, here we're borrowing 1. Okay? And that means how many bits are left, and right here, If we're borrowing 1 to the network, that means there's 2 to the 7th left over for the hosts. That means there's 128 hosts per network. Let me just see. Let me just put in another information. 0 networks. 0 subnetworks. And that's equal to 2 to the 8th, 256 total hosts. And 254 usable hosts. Okay? If it's slash 25, okay, that means 7 bits available for the host per network, and at slash 25, okay, we're borrowing 1, so there is 2 networks that are created. So 2 sub networks, and that is equal to, because we're borrowing 1, that means there's only 1 left over. Well, there's only 1 being used for the network. 7 are, oh my gosh. 1 second. Okay. Okay, 7 are available to us, and that's 128 usable, 128 total hosts per network. And that is 126 usable hosts. Now you get wow, that was a big drop. But you see the effect of even borrowing 1 bit. Okay? Now if we go all the way to borrowing 3, okay, so that is slash 27. So that is borrowing 3, and that is 8 subnetworks because it's 2 to the 3rd. And 8 minus 3 is 2 to the 5th equals 32 total. And I'm just going to say 30 usable hosts. We already decided that. But how many hosts do we need here? We only need 2. And it will never change. And again, also going back to my analogy right here, if we have 8 dedicated to the hosts, 254 usable hosts, so it's the whole thing. If we borrow 1, leaving 7, that's 126 usable hosts, so that's 2 networks. I should have put 2n, 0n, 8n, for example. And I might as well just, for the heck of it, do slash 26. That means 6 are available. That means 4 networks, sub-networks, 4 subs, and that is equal to 2 to the 6 that are dedicated to the hosts, and that is 64 total hosts, and that is 62 usable or available hosts. 2 to the 5th is 30 usable. And if we go all the way down, all we need is 2. So we don't have to finish this. And just so you know, 128 usable hosts, so we can actually, sorry about that, I keep on skipping around because everything seems like they're related in networking, and they are actually. So here we have 2 networks, so we actually divvy it up in 2, and we have 128 on this side, and 128 on this side. Okay, that's this one. Now if we borrow 2, meaning there's 6 left over for those, 64 total hosts. So now we'll do this in orange. And as I said, we did this in blue. Let me just put an arrow right here. We'll do this one in orange. Now we go this way and this way. So we have 64, 64, 64, 64. Here, if with 32s, we'll do this one. Red. So it's multiple networks. So like do this, do this, do this, and do this. And I'm not going to do all 30. Each network is now 32. So 32, 30. You get the idea. So the overall pattern is that as we increase networks, the hosts per networks are reduced. Consequently, the more hosts per network we have, the more hosts per network that we have, the less networks that there will be. So the idea is here, if we go back, if we want to look at these transmitting networks, these are called essentially. Let me just point to point. They are also called transport networks. Now, transport networks are great because you can have a multiplicity of routers right here. Oh, sorry about this. Let me redo this better. So you can have a bunch of routers here, here, and here. And then you can have one big powerful router here. And you can have some T1 lines between each router. And then each router goes to its LAN. And so what you can do is you can maximize your host on this side, and all you got to do is have 2 hosts per network here. So what you can do is you can say, wait a second, if I'm borrowing 3, and so that's going to be 30 hosts per network, I can, instead of breaking it down like that, let's say, for example, I can analyze my network like this. And let's say I want 8, there's going to be 8 networks. So 1, 2, like this. That's way more than 8. Sorry about that. Let me erase that. Okay, so there's my 8 networks. So this could be, this is my dot 0. That's my dot 32. So this could be dot 0. That's my dot 32. That's my dot 64. Okay, so I can have 30 hosts here, 30 hosts here, and then the dot 64, 30 hosts here. And now what I can do, I can make a special transport. I could say dot 96 is my transport subnet. And in my transport subnet, I can divvy that up. So I can start at 96. And then I could say, okay, so what's my next network? If I'm only doing 2 hosts per network, what is my next network? Let's take a look at this. So if I'm only doing 2 hosts per network, I want to reserve 2 hosts for the network. Okay, how many bits am I reserving for the network? For 2 hosts for the network? Okay, how many hosts in all am I going to need? I'll put you, if I only need 2 IP addresses on this transport network, for this transport network, because it's only point to point, I'm only going to need 2 IP addresses. So how many total bits per network am I going to have to reserve for the hosts? Two bits, because two bits will yield four IPs per network. And because we can't use a broadcast or the network, out of those 4, we can only use 2, and that's perfect. So that's 2. Now this is going to be really, really strange. If we only need 2 bits for the hosts, which is what this says, host, all the rest are going to be for the network. So believe it or not, it's no longer /27. Okay, that's your mama's subnet mask. We ain't in Kansas anymore. When you're dealing with a transport link, you're doing /25, /26, /27, /28, /29, /30. So typical transport links are /30. Boom. /30. And what is that translated into decimal? 252. Because here's why. When you're doing /30, okay, basically it's, and I'm going to get out of the drawing tool right here. Let me just do this. It's 255.255.255.252 because it is, let me go back to the home right here. Let me go back to, I'm just going to reduce this to 8. It's 128 plus 64 plus 32 plus 16 plus 8 plus 4. And that's where you get 252. So now we have to communicate the fact that we don't need 30 hosts for this transport network. It's kind of like, would you want to, let's say you were buying a car from somebody off of Facebook Marketplace and you want to look at the car. Are you going to wear a tuxedo? No, that's too much work. So if all we have is a transport network, are we going to want 30 hosts? No, that's a waste. We only want 2 hosts, which is what? .252, which is /30. So how do we communicate 252? All we have to do is now go to these inside interfaces, okay, and change the IP address subnet mask from 224 to 252, and we're going to do that right now, really quickly. conf t and interface F0/0 and let's see the we can do show run, And we can verify that 10 or 00 is actually .33. So let's go ahead and change this to 252. So IP address 192.168.1.33, 255, 255, 255.252. End. Let's do a show run again. And we can now see that the 32 network is 252. Now, we're going to have to go and change this IP address, even because if we do a show run, FA00, which is the 32 network, is .62 224. We need to change this to 34 and that to 224. And we're going to do that now. Now, conft interface F0/0 and IP address 192.168.1.34 255, 255, 255, 252. Okay, we have successfully schemed this up so we're not wasting IP addresses. But here's a problem. If we go again, if we go to show IP, we do a show IP route. Let me just do show IP route. Whoa! Where did our route go? Where did the route that we learned from RIP, where did that go? It went because of the weakness of RIP. Now, I told you before, there are several routing protocols that are out there. Okay? There's RIP, IGRP, and so on. The problem with RIP is that it was from a time in the late 60s that there just weren't a lot of routers around. And subnetting only came into play in the mid to late 80s when we began to run, or when they predicted we would be running out of IPv4 IP addresses, because there was a time when every connection was point to point, so there was no need for subnetting. So you have an AOL connect. You ask your dad about AOL. Ask your parents about AOL. They probably use AOL. Well, that was like a point-to-point connection. There were no internal networks because very few computers were actually connected to the internet. It was only when the late 80s, early 90s happened, when more and more people were online, that there necessitated the notion of subnetting. If you don't have subnetting and you're using a routing protocol, well, if you have subnetting and you're using a routing protocol that doesn't understand about subnetting, it is not going to succeed. So let's take a look. Let's do show IP protocols. And let's see, it's still routing protocol RIP. It's still routing. You see, because it's still using RIP as its routing protocol. And it's using version 1. Routing for networks 192.168.1.0. So it does understand these various network things, but what do you think is it's if it only understands the fact that networks are divvied up into 32s, why was, when I did 252, why did it disrupt the routing protocols? Can somebody tell me? Well, let me ask
Is it
you.
because
Yes, go on.
I was
Tell me.
gonna say, was it because you changed how many networks you was using?
Yes. So what if I told you that we're going to the Cheeseburger Fest in Port Austin, and everything's going to cost $5. So if you order one burger, it's $5. If you order two cheeseburgers, it's $10 because it's a multiple of 5. And what if I said, yeah, if you order a cheeseburger, fries, and Coke, every single solitary item is $5. So if I said if every item is $5, how much will a cheeseburger, fries, and Coke cost there?
$15.
Right, and that's fine. Everything that we had done previously is in batches of 32s, 0, 32, 64, 96. But what if, okay, mind you, what if you go to the Cheeseburger Festival and there's some random item that only costs $1, and in here you're sitting with all 5s? Okay? And nobody has a single, so nobody can give you change. You be messed up, right? So think of Rip as the guy who only brings 5, 10, 15, or $20 with him. All he brings is $5 bills, and all he understands is $5 bills. So if something costs $6, he's screwed. He doesn't understand. His thing is overloaded. His brain is overloaded. So what we need now is another routing protocol that understands not only this part, the one part of the IP address, but it also understands that, hey, there's a subnet mask involved too. So the problem with RIP is the only thing it broadcasts out, okay, is the IP address. It doesn't send out the subnet mask too. So we need a routing protocol that not only broadcasts the network and the interfaces attached to that network, but it also sends out the subnet mask. And thank God there's such a thing as RIP version 2. So there's RIP, which is implicitly called RIP version 1. And then there's RIP v2 or version 2. And because we're using an enhanced version of RIP, it also sends out the subnet mask. So if you want to have, and just so you know, what we just did here was something called VLSM, Variable Length Subnet Masking. So RIP or RIP v1, however you want to say it, and it just stands for Routing Internet Protocol. It was really one of the first routing protocols that there was out there in the 60s. Now, keep in mind, some of you are like in the 60s, but keep in mind, at that time, it was a huge innovation in the world of networking. Imagine a world without any networking protocols. We couldn't go to Google, we couldn't go to Facebook, we couldn't go to Amazon, we couldn't go to, anywhere else. We couldn't go to TikTok and all these other places. But there is a need for variable length subnet masking because, quite frankly, it is wasteful to have something like a transport link having 30 hosts, having an IP block being 30 hosts, because it's such a waste. Because when you go back here, we might need these guys. We might need all these people. We might need all these hosts. We might need all these networks eventually. Do we want to waste these networks on just a transport link? No. We want to break up, let's say, the 96 one into little subnets of 4 IP addresses, okay? And that way the whole, just the .64 could be just for transport links. Okay? But the problem now is we have to route them so PC0 can get to .65. So all we have to do is change the routing protocol, and I promise this will be the last thing. So let's go ahead and do configuration terminal, and then router rip. Okay. Now again, if we do a show run, we can see that, IP class. Oh, router. We have the router rip already in here. It does show the network, but this time we're going to do version 2. That's it. That's it. And then we're going to do the same thing on this side, version 2. Conf t router rip, and we can do a show run, and we can see that we do have the network already listed under router rip. All we have to do is version 2, and that's good. Now we can go back to this router, the first router, show IP route, and it has not shown up yet. Sorry about that. It might need some time. Let's do show IP route, and the route does appear on this side. Let's go back to this one again. Show IP route, and lo and behold, it shows up on this side. And we can do show IP protocols, and we can see now that, look at that, default version, send version 2, receive version 2. So now we can see that we're actually seeing, we're doing RIP v2. So the routing protocol is still RIP, but it says sending version 2. Remember how it said version 1 before? Now we're sending version 2. So now we go to this PC, 65, and it pings. Okay. So I would like to know, what can I do to help you? I can upload both this recording, and I can also upload this packet tracer topology I have. Does everyone want me to do that?
Yes, please. Yes.
Okay. All right. That's it for today. Everyone have a good day, and if you would like, take a ganders at the recording here, and I'm not going to edit it. I'm just going to upload it as it is and call it good. Okay? Everyone have a good day.
All right, you have a good one.